Hi, this is group B32 and we're going to talk about cardinality. The definition of cardinality: let S be a set if there are n distinct elements in S where n is a non-negative integer. Then we say that S is a finite set and n is the cardinality of S. However, sometimes the number of elements of a set is uncountable, like the set of odd positive integers or odd real numbers between 1 and 2. We will talk about this kind of set soon. For a countable set, we use this symbol to denote the cardinality. Here are some notable cardinalities. For an empty set, the cardinality is 0. For the power set of a set, the cardinality is 2 to the cardinality of the set. The set of integers has infinite but countable cardinality, and the real number set has infinite and uncountable cardinality.
Cardinality of Cartesian products. A Cartesian product is denoted by A times B and is equal to the set of elements A and B such that A is an element in set A and B is an element in set B. For example, let's have set A equal to the number 1, and let's have set B equal to the numbers 2 and 3. The Cartesian product of A and B would be equal to 1, 2, the set 1, 2, and the set 1 and 3. Now the cardinality of a Cartesian product is equal to the cardinality of the first set times the cardinality of the second set. For example, the cardinality of our first set is 1. The cardinality of our second set is 2. And the cardinality of our Cartesian product is 2. If we go by the formula, 1 times 2 is 2, which is the cardinality of our Cartesian product. And as you can see, our Cartesian product has 2 elements, the set of 1 and 2 and the set of 1 and 3. And A has 1 element and B has 2 elements. Therefore, the cardinality of our Cartesian product is equal to the cardinality of the first set times the cardinality of the second set. Cardinality of power sets. A power set is denoted by P of S and consists of all the subsets of the set S. For example, if the set S is equal to 0 and 1, the power set of S is equal to not, the set of 0, the set of 1, and the set of 0, 1, because these are all subsets of the set S. Now the cardinality of the power set of S is equal to the formula 2 to the power of S, where S is also the cardinality of a set. For example, in our set, the cardinality is equal to 2 because there are 2 elements. And the cardinality of our power set is equal to 4 because there are 4 elements. Now if we go by the formula, 2 to the power of S is equal to 2 to the power of 2, which is equal to 4, which is equal to the cardinality of our power set. This proves that 2 to the S is equal to the cardinality of a power set.
One interesting property of cardinality is the ability to count an infinite set of numbers. Although this may seem impossible, we're going to prove this through a technique known as Cantor Diagonalization. We begin this by first making a grid of rational numbers. As a quick refresher, a rational number is a number that can be written as some integer p over some other integer q. That is what differentiates it from an irrational number. So we'll first begin by listing all of our numbers with a denominator of 1. So 1 over 1, 2 over 1, 3 over 1, and so on. Next with 2, and then 3, 4, and do this forever. So what we want to do is arrange our positive numbers so that way we cover every possible number. So what we will first do is list all the numbers where p plus q is equal to 2. Once we have done that, we'll do all numbers where p plus q is equal to 3, and then so on. So we begin at our grid, top left corner at 1 over 1. And every time we reach a unique value, we're going to circle it. So since 1 over 1 is our first value, it's obviously unique, and we're going to circle it. Next, we'll move down, and we set to 1/2. We do not have a value of 1/2, so we'll circle it, and then continue to move up in a diagonal line. And then get to 2 over 1, circle it, move over, and continue in this pattern. Now as we reach 2 over 2, we had our first number with a repeating value. Since 2 over 2 is the same value as 1 over 1, or just simply 1. So we just skip over it, and continue moving down to 1 over 3, which we circle, and we continue to do this forever. Now as we begin, once we would have finished doing this, infinitely, we can then list our numbers. So first we have 1 over 1, or just 1. Next we have 1/2, then 2, and 3, and then we skip over 2 over 2, and then we have 1/3, and this will continue forever. Because these numbers, or the circled numbers, can all be listed exactly one time, we have shown that the set of positive rational numbers is in fact countable. And this countability of countable but still being infinite is denoted by the symbol of the Hebrew letter Aleph with a subset of 0, or Aleph null. And that is how we count an infinite set of numbers. Yeah.
For our next example, we'll show that the set of all real numbers has a cardinality that is uncountable. We will do this using a proof by contradiction. So we state the negation of our original statement that would be that the statement that the set of all real numbers is countable. This will lead us to a contradiction. So we know that the subset of all real numbers from 0 to 1 must also be countable, since the entire set is countable. Under this assumption, the real numbers between 0 and 1 can be listed in some order, say R1, R2, R3, R4, etc., such that all the real numbers between 0 and 1 will be included in this list. So we'll let the decimal representation of these real numbers be, say, R1 equals 0.D11, D12, D13, D14, etc., such that Dij is an integer between 0 and 9. So for instance, if we have R1 equals 0.235, we have D11 is equal to 2, D12 is equal to 3, and D13 is equal to 5. So now we can define a new real number R, such that R is equal to 0.D1, D2, D3, etc. And Di is equal to 4 if Dii from our original set of numbers does not equal 4, and 5 if Dii does equal 4. So now we know that every real number has a unique decimal expansion when we exclude the possibility that the number is 0.99999, such that the tail end consists entirely of 9s. Therefore, the real number R is not equal to any of these numbers, R1, R3, etc. because the decimal expansion of r differs from the decimal expansion of ri in the ith place to the right of the decimal point for each I. So d11, d22, d33, d44, etc. Because we use this definition here where if dii is 4, then we make it 5, and if dii is not 4, then we make it 4. So now we know that r is not equal to any of these real numbers, r1, r2, r3, etc. So now we know that this number r cannot be in this list of numbers ri. But before we said that this list contained every single real number between 0 and 1. So we've reached a contradiction. So this must mean that the set of real numbers between 0 and 1 is not countable. And now if we know that the set of real numbers between 0 and 1 is not countable, we know that the set of all real numbers must also be uncountable. Hence, the set of real numbers is uncountable.
This has been our presentation on cardinality. Thank you for watching.